Good evening, everybody. My name's Bob Hill. I'm the Executive Dean of the Faculty of Sciences at the University of Adelaide. I'd like to start by acknowledging the Kaurna people, the original custodians of the Adelaide Plains, and the land on which the University of Adelaide's campuses at North Terrace, Waite, Roseworthy and Theberton are built. Well, welcome everyone to tonight's Research Tuesday event, and it's also our third inaugural lecture for the year. This year our Research Tuesdays program is incorporating a series of inaugural lectures, and these lectures are held to mark a major milestone in our researchers' careers, such as achieving the rank of professor or being appointed to a chair or other professorship. Tonight we welcome Professor Sandy Steacy, who's head of our new School of Physical Sciences. Sandy came to the University of Adelaide from the University of Ulster in Northern Ireland, where she was Professor of Earthquake Physics and the Director of the Environmental Sciences Research Institute. She did her undergraduate degree in geology at the University of North Carolina at Chapel Hill and her PhD in geophysics at the University of Southern California. Her PhD research involved understanding the relationship between earthquakes and the highly crushed rocks found along fault zones. Her development of a model explaining the fractal geometry of these rocks was published in Nature while she was still a student. Sandy's more recent research has been focused on understanding how earthquake hazard changes with time. She's led a number of international collaborations on this topic, and in 2005 was an author on a Nature paper which identified the likely location of a large earthquake offshore Sumatra. The expected earthquake happened 11 days after the paper was published. If she predicts an earthquake for Adelaide tonight, I suggest you be very, very concerned. Sandy was lead editor of a special issue of the Journal of Geophysical Research on earthquake triggering and lead convener of a European conference on earthquake processes. Over the past few years, she's been working on earthquake hazard in New Zealand. She was a member of the expert elicitation panel whose work informed the development of new building codes following the Christchurch earthquake, and she's a visiting scientist at GNS Science near Wellington. Will you please join me in welcoming Sandy Steacy. Thanks, Sandy.
Thanks, Bob. Thanks, everybody. As Bob has alluded to, and as you'll be able to tell very quickly from my accent, I'm an American, and I grew up in California, near San Francisco. And so I'm starting with this picture. This is from the 1906 California earthquake and fire. And this is quite an interesting earthquake for a couple of reasons. The first is that it really gave us our first understanding of how earthquakes work, and I'll talk about that in a second. The second is it really exemplifies the interplay between science and society. And you might not think that, but when I was a kid growing up, we were always told that the fires were a direct result of the earthquake. In other words, that the gas lines were broken during the earthquake, there was some ignition source or sources, and you got these fires. But it turns out that later studies showed that a lot of those fires were lit or occurred much later. And the assumption is they were deliberately set. And when societal information comes into that is that in 1906 in California, nobody had earthquake insurance, but they did have fire insurance. So in terms of the science then, this is what we know now about the 1906 earthquake. It ruptured the San Andreas Fault. This is San Francisco. It started near there. The red and the orange is areas that experienced a lot of shaking. The blue had very little shaking as you get further away from the fault. We now know something about plate tectonics, which I'll remind you of in a second. But basically, this is the North American plate. This is the Pacific plate, which is moving north relative to North America. So the earthquake happened along here. And this earthquake was extensively studied by Henry Fielding Reid, and he was a scientist in the East Coast, but he was invited to join the California Commission. He was the only non-Californian on it, and he's the one who really put together what happened. And he did this by very, very careful mapping of the earthquake and of its effects. And so this is Point Reyes National Seashore, Balloonist, just north of San Francisco. This fence used to be straight. The earthquake came along, that's the San Andreas Fault right there. So it offset that fence by about 3 meters, and the farmer just came along and added some rails and fixed it. Okay? But from this type of mapping, Reed really worked out what happened during that earthquake, and it came up with the whole idea that earthquakes occurred on faults. And he also came up with a model called elastic rebound, which talks about how the stress builds up, and then let's see if this is going to work. No? Okay. Aha. That stress builds up, and it's stuck right at the fault zone. Stress builds up, builds up, builds up over time, and this is over a couple hundred years, allegedly. You can see this is something like that fence. Then boom, you get an earthquake, and you get a sudden slip. Okay? And so there's the originally straight fence right there, and there's your fault zone. Okay? And notice the deformation here at the edges, because that's something that we'll come back to. So just to put this in context, most people have probably heard about plate tectonics, but the basic idea is that the surface of the Earth is divided into a number of thin plates. They're about 100 kilometers thick, and they move with respect to each other. And this is where most earthquakes happen. And so in some places they move side by side. So here's the San Andreas Fault, there's North America, there's the Pacific. Okay? In other places, they pull apart, like the Mid-Atlantic Ridge, and so the Atlantic Ocean is getting bigger. When I was in Ireland, we always would joke that we were getting a few centimeters further away from North America every year. Some places, they run into each other, and you get subduction. This is Japan, for example. You get one plate going under another. You get volcanoes. You get very big earthquakes. And other places, you have two continents running into each other, and this is like India slamming into Eurasia, where you had the Nepal earthquake just last month. Okay, so that's the basics. That's where earthquakes happen. One of the other things that Reed figured out was that it wasn't the earthquake itself that caused all the damage, but it was waves as a result of that. So you had this sudden slip, and it generated waves. And this is a typical seismogram. It's showing two of the three major waves that you get. So the initial thing you get is a P wave, and the P wave vibrates in the same direction that it propagates. But it turns out that the velocity increases with depth. And so if there's an earthquake over there and I'm standing here, I don't feel the seismic wave that propagates along the surface. I feel something that comes down, comes back up, and kicks me in the bottom of my feet. Okay? So when I was a kid growing up near San Francisco, I was taking an exam one time, and suddenly everybody in the room turned around to the person behind him and said, "Stop kicking my desk." Because that's exactly what it felt like. And then a couple seconds later, we got the S wave, and the S wave vibrates perpendicular to the direction it propagates, so it started shaking us side by side, at which point we went under our desks. And we were too close to feel the surface waves. But if you're far enough away, about 100 kilometers away, and if the earthquake's pretty shallow, then you get a rolling motion, and these are surface waves. And so in the Nepal earthquake, there were reports of people feeling a very, very long rolling motion. Okay, those are surface waves in Kathmandu. So it's these seismic waves that cause most of the damage, and it's also how we measure the size of the size of an earthquake. So most people have heard about the Richter Scale, and so they'll talk about a magnitude 6 earthquake or magnitude 8 earthquake. Two important things to realize about this. The first is that in terms of amplitude, the difference between a 6 and a 7 is a factor of 10. The difference between a 6 and an 8 is 10 times 10, or a factor of 100. So that's the amplitude of the seismic waves that gives you the shaking. But in terms of the energy release, it's a factor of 30. Okay, so the difference between a 6 and a 7 is a factor of 30, a 6 and an 8 is 900. Okay, so the big ones are the ones that count in terms of damage, mostly. So is construction. So just a few pictures. This is the Haiti earthquake in 2010. You may remember this. This was a terrible earthquake. It badly affected Port-au-Prince. It was only magnitude 7, but it killed between 250 and 300,000 people. Okay, and it's basically construction. So you can see here lots and lots of unreinforced masonry. Unreinforced masonry does not do well at earthquakes. Plus you had things on slopes. If one building collapsed, it then collapsed what was downhill from it. This is Padam. This was a smaller earthquake. This is a 6.6 in southern Iran. First large earthquake down there for thousands of years, and basically destroyed Padam, killed about 30,000 people. Okay, this is just adobe clay houses, no resistance to earthquake shaking whatsoever. So it's a bit of a truism amongst earthquake scientists that it's not earthquakes that kill people, it's buildings. because most people die when buildings fall on them. But that's not completely true, because there's also what we call secondary hazards. One being landslides, and this is Nepal. This is the, I can't remember the name, but this is the valley where there were a lot of trekkers that were killed, and obviously a lot of Nepalese as well. So a very large landslide. And this is then another secondary hazard, tsunami. And this is the Tohoku earthquake, a magnitude 9.0. Okay, so in Japan, because the buildings are very well constructed to withstand earthquakes, a lot of the buildings, or most of the buildings, stood up to the earthquake itself, and then, as you can see, they were wiped out in the tsunami. So the question is, what can we do? And we've all seen the movies, and particularly growing up in California, we saw lots of these movies, and I'm told that there's a new one just coming out, San Andreas or something like that. But we've all seen these movies, and somebody figures out that the big one's about to come. And it's some bright, young, enthusiastic scientist, usually a woman, which I quite like, but nobody will listen to her. And nothing happens, and the earthquake happens, and then you have some big, strong man who has to go and save everybody's lives. But in earthquakes, you know, we talk about prediction a lot, and these movies always talk about prediction. But as an earthquake scientist, I get a little bit picky about that word, because to me, as an earthquake scientist, prediction means we're going to have a magnitude 8 earthquake next Tuesday at 2 o'clock in Dublin. Okay, and I'm not making that prediction, but that's what a prediction is. Okay, it's not that, oh, I think an earthquake's going to happen, or eventually there's going to be an earthquake, or a 6 is inevitable at some time in New Zealand. Okay, that's not a prediction. It's, you know, it's a truism, really. Okay, so this is what we mean by prediction. And so the question is, can we predict earthquakes? You know, are the movies right? Can we predict earthquakes? So let's look through a few examples. This is the San Andreas Fault. We're now in Southern California. And these are the San Bernardino Mountains. The fault runs basically right along there. Okay, it's the southern part of the San Andreas Fault. And think about Reed again. Think about elastic rebound. Simple picture. Stress builds up, builds up, builds up. Earthquake happens. So if we know the rate at which the stress is building up, we know about how much it slips in an earthquake, then we should know roughly how often the earthquakes happen. Okay? And then maybe we can start monitoring things, trying to look for things that would tell us an earthquake is going to occur. The thing is, it's not that simple. So this is a fault map of Southern California. Here's the San Andreas there on the fault map. Okay? And there's a lot else going on. There's a lot of other faults. And these faults interact with each other. And so it means that you don't get this simple picture of a fault in isolation with the stress building up, but you get a fault, something happening in one fault affecting another fault affecting another fault affecting the first one. Okay, and we'll talk more about that. So it's a tricky picture. And when you actually go and look at the data, you don't get anything like a regular time between earthquakes. So this is some work, again, from Southern California, Carrie C. And these are the times of old earthquakes. So this was the most recent. This was 1857. One before that was in 1812, and we got that off of tree rings, actually. And then here's a bunch of older ones that are from trenches that were dug across the San Andreas Fault. And what you see is that there's a lot of irregularity in the timing of those. And it's kind of funny because I did my PhD in Southern California in the late 80s. And the last big earthquake had been in 1857. So we're told it's due, because the recurrence time is 130 years. And if you take that data, I mean, I guess you could fit a straight line to it. Standard deviation is 100 years, but you could fit a straight line to it. So we don't get that regularity. Okay, and that's one of the really important things. We can't say, just because it's been so many years since the last one, the next one's due. Another complication in this is that we're interested in the big earthquakes. Remember, the difference between a 6 and an 8 is 900 times the amount of energy released. But for every big earthquake, we get a lot of little ones. Okay, so for every 7, we get 10 6s, we get 100 5s, we get 1,000 4s, we get 10,000 3s. Okay, and that's globally. Okay, this is called the Gutenberg-Richter relationship. So this is the log of the number of the earthquake as a function of the size, and since that's a log scale, it's log, straight line. Okay, so again, the take-home message is we get lots and lots of little earthquakes for every big earthquake. But if we're going to predict, we need to be able to predict the big earthquake, because we don't want to evacuate this room because we're going to have a magnitude 2. Okay, we want to evacuate because we're going to have a 5.5. Okay, so how do we know that, or can we know that? Going back just to this fault map, if you look at this, you see some very big faults, and the San Andreas goes way up there. You see a big fault here, the Garlock. You see some littler ones here, and you can imagine if you zoom in on that, you zoom in, and you see the faults repeating at smaller and smaller scales. And that's indeed what we see. So fault networks are fractal. Okay, in other words, they're self-similar. They look the same at every scale. And that's really true about geology. So anybody who does any geology at all is taught from day one, you never take a photo of a geologic feature without having a scale bar in it. Because without a scale, you can't tell if that's a little piece of rock, or it's something like that, or it's the side of a mountain. Okay? So we know that at big scale, geology is fractal, it's self-similar. And we also know it at small scale. And Bob made a reference to this paper where we were looking at crushed up rock within fault zones, and it's fractal. So if you look at the size, frequency distribution, just like for earthquakes, we find that you get lots of little particles for every big particle, and it follows a parallel. Okay? And that has implications for how earthquakes work. So this is a model that I developed with a colleague a number of years ago, where we tried putting in just a fractal distribution of strength. And so these red and orange patches here are places that are very, very strong on a fault zone. Blue are places that are very, very weak. And what we have here is a snapshot of the stress. So this is basically scars of old earthquakes. So this is a place that had an earthquake about that big sometime in the past, and it's now recovered a lot of stress. So the fault's been moving since and building up stress on it. This is a place that had an earthquake quite recently, doesn't have much stress on it. And then these high colors right at the edges are stress concentrations, because if you break something, you concentrate stress at the ends. Okay? So in that model, we said, well, what do the earthquakes look like? And you can kind of get an idea just looking at this, that you get a lot of little ones and a few big ones. And this is a big one that's going to happen. But you see how it grows very, very irregularly. And it circles around and eventually wipes out that strong patch. Now, I could have picked a different earthquake and it would have gone nowhere. It would have failed one cell or only a couple of cells, okay? Which is what we see. And so what we think happens with earthquakes is that basically all earthquakes start off the same. So they start to grow, and they either run into something that makes it easy for them to keep going, like in that rupture, or they run into something that stops it. So if we're going to predict earthquakes, we've got to know what the stress conditions are like and the strength conditions are like everywhere in the fault zone. Because we have to know not only are you going to have an earthquake tomorrow, but how big it's going to be. Doing that is really, really difficult, as you can imagine. Faults are very, very long. So we're looking at the San Andreas again. It's a great fault. We're now up here in Central California. I don't think I even have to point out the San Andreas. And we've got a fault that's 1,000 kilometers long, 15 kilometers deep. Most earthquakes start deep. In strike slip areas, this type of environment, they start about 15 kilometers deep. So how do you measure that? We can't. Okay, what about precursors? We see that in the movies, right? You get precursors, something happens, something changes and tells you that you're going to have an earthquake. So the USGS, the U.S. Geological Survey, did a study for precursors. And the idea, it was quite a neat one actually, because the issue is you've got this 1,000-kilometer long fault, where do you look? Where do you put your instruments? What they said was, well, look, we've had two earthquakes that did pretty much the same thing. In 1934 and 1966, we had earthquakes that started here in this part of the San Andreas, and they broke to the south. And they were both about 30 kilometers long, and they were both magnitude 6. So if we put our instruments out there, and that's all these orange squares, we put our instruments out there, we just have to wait for the next one. And even better, they knew when the next one was going to be, because they said the earthquakes are really regular in time. So here's the events going back. This is 1966, that's 1922, et cetera, et cetera. And they're perfectly regular, well, except for 1934, which happened early, but we'll ignore that. So they put all their instruments out, every instrument you could possibly imagine, and waited. And they waited some more, and they put out more instruments because they had time and kept getting funding. And it turned into a whole cottage industry for the town of Parkfield. This is a village of about 200 people, which called itself the earthquake capital of the world, which I thought was a bit pretentious. Their whole economy ended up revolving around all the scientists that were coming there to maintain the instruments, and then all the geology field trips that were coming to show the students the instruments that were there waiting for the earthquake. So the earthquake was supposed to happen in 1988, and eventually it did in 2004. So it was a bit late, but it did happen, and it's still a good experiment. Did it capture anything? Well, the first indication that things may be a little bit strange was that it started to the south and went to the north, and it was supposed to start to the north and go to the south. But that's okay, that doesn't say anything about precursors, and you've still got all this instrumentation here that should have captured any precursors, and they found nothing, no precursors, okay? Now it's only one event, but we've never had good documented evidence of precursors, even though it makes for great TV or great movies. So the USGS thought this was a great success, of course, because they'd spent I don't know how much money on it, and it was, I think, because it showed that the model that they proposed didn't work. But it wasn't a tremendous success in terms of saying these are precursors that we see before earthquakes. So the upshot of all of that is that I would say with a high degree of confidence that earthquake prediction next Thursday at 2 o'clock doesn't work. Okay? So then the question is, can we do anything? We know plate tectonics. We've got areas of high hazard. Okay, basically the plate boundaries. Is it just engineering? Do we just build the strong buildings that won't fall down? That's one solution. Of course, it costs a lot of money. And so if you're in Turkey, and we've done some work in Turkey, and you've got a huge, long, 1,200 kilometer long fault zone, and you've got limited resources, where do you target your resource? Where do you upgrade? Where do you spend the money doing the retrofitting? Okay, so it's something we can do better. And I think we can. And this is, back to our friend elastic rebound, right, from Henry Reed. This is our fence again. This is before the stretching has happened. This is after the earthquake. These are the areas where the stress is increased. And we can actually calculate that. And I'll not go through it, but basically stress is a tensor. We can calculate that from knowing the slip right here on that earthquake. And then we can say, well, what are the faults we're interested in? And we can take that awful tensor and we can say, well, what's the shear stress parallel to the fault? In other words, the stress that's going to make the fault slip. And what's the stress that's holding it stuck together? Okay? We can calculate that, and we can make pretty maps like this. So this is the Landers earthquake. This is a 6.6 aftershock. So this was a 7.2. The redder areas, this is California, where the stress increased as a result of that, and the white dots are aftershocks. Okay? Aftershocks have been in the news a lot lately after Nepal. Aftershocks, it's kind of an artificial word. Basically, aftershocks are simply smaller earthquakes that happen after a large event did and are expected to be causally linked. In other words, they were triggered by it. So you have your slip and you don't get uniform slips, so maybe this bit moves 3 meters and this bit moves 1 meter and that bit moves 1.5 meters, and then you get little earthquakes trying to catch up. And then you get these stress changes out to the edges and you get these aftershocks as well, okay? Aftershocks are terrible for the people in the area because in Nepal, for example, people don't know, do they go back inside, do they not go back outside, or not go back inside? They're terrifying. They bring down structures that are already weakened. I mean, they're bad news and they're natural, and so we did a lot of work when I was at Ulster on aftershocks, but also on whether we could very quickly make maps like this. And we led a European project on this, and the idea was if we could identify with confidence these types of areas, you might say something meaningful for the disaster response. In other words, could you say, build your emergency shelters here? You know, site the displaced people here because they're not going to get much shaking. Don't site them here because they are going to. That type of stuff. And as a result of that work, we were really prepared to react after the Indonesian earthquake, the 2004 Sumatran earthquake. And you remember this was a 9.3. It ruptured from sort of northern Sumatra up into the Indian Ocean. It's about 1,200 kilometers long, generated a tsunami that killed about 200,000 people in Banda Aceh and northern Sumatra. And the tsunami, because there wasn't a tsunami warning system in the Indian Ocean, it killed people in India and Africa as well, so in Sri Lanka. What we did is after that earthquake is we calculated the stress changes and we said, well, it's increased stress on the Sumatra fault that runs down the middle of the island, and it's also increased stress along the subduction zone. And we're really worried about that because we wanted people to realize that the chance of a big earthquake hadn't gone away, that there was potential for another big earthquake. And this is the one that Bob referred to in his introduction. So this paper came out on St. Patrick's Day, 2005, and 11 days later there was magnitude 8.7 there. I spent the entire next day on the telephone saying to reporter after reporter, we did not predict that earthquake, because we didn't. We had indicated an area of risk. We hadn't put a magnitude on it, we hadn't put a time on it, and we hadn't put any numbers to it. We had just indicated an area of risk. It was not a prediction. I think we got that across, but it took a little bit of doing. So just to show you what happened, because that earthquake was fortunately that earthquake didn't generate a large tsunami. And the reason is that most of the displacement was underneath Nias Island, which is right here. And so this is kind of the subduction zone version of Reed's elastic rebound, where you've got one plate going underneath another. It's stuck. As it's stuck, it's pulling the overlying bit down with it, okay, because it's stuck at that fault zone. And this is Nias Island prior to the earthquake. This is January 2005. And you can see these straight lines of trees or drowned trees. Okay, that's a plantation. And that plantation was planted on dry land 100 or 150 years previously. And then it was being progressively pulled down along the subduction zone. And then the Nias earthquake happened. And that's May 2005. And I'll pop back up. Okay, so that's like the offset of that fence. But because most of that happened underneath the island, you didn't get a big tsunami. So following that earthquake, this is 2004, this is 2005, we played the same game and we said, well, it's increased stress further down the subduction zone, it's increased stress further on the fault, and then we decided to go into tsunami modeling. Why not? And we actually had a motivation for that, and this is Padam. This is the area that would be affected by the next earthquake if it occurred where we're worried about, kind of in here. You can just see how low-lying it is. You've got millions of people that are vulnerable to tsunami. So we went into modeling and we said, well, we can make a whole bunch of synthetic earthquakes. We can calculate the seabed displacement as a result of those earthquakes. And we can calculate the tsunami wave heights. And so this is for 25 simulations of possible earthquakes, red being the maximum height, blue being the minimum, and black being the median. Engineers and policymakers hate pictures like that because they want one number, and we couldn't give them one number, okay? And that is relevant to what I'm doing now. But we did all that, and then we sat back, we published this, we waited for the earthquake, and we waited, and we waited, and we're 10 years on, it still hasn't happened. So sometimes it works, sometimes it doesn't. It's what makes science fun. Okay, moving back to aftershocks and on to a place closer to home. This is Christchurch, it's Canterbury. And this was a sequence of 4 earthquakes. The first earthquake was in September 2010. This was the Darfield earthquake. 7.1. Slipped at least 6 faults, and green here is where it started. This is the epicenter. This is where most of the slip happened on this red fault here. And the green dots or circles are the aftershocks of that up until the time of the next big earthquake. Okay? And that next big earthquake was the Christchurch earthquake. So that's in red, and the stars somewhere in here. There we go. And then aftershocks, and then the blues, the next one in June, and then those were the December earthquakes. Okay, so a whole series of earthquakes that appeared to be triggered And when we play this Coulomb game, so going back to that picture I showed you where you calculate the stress change because you know the slip on the earthquake, and you then just make one of these lovely red and blue maps, and you say, well, where did the aftershocks happen? This is the the September 2010 earthquake, okay? And the yellows are the aftershocks that happened between that and the Christchurch earthquake. And that star right there is the Christchurch earthquake. Okay, so it's consistent with being triggered by this earthquake. Do the same thing, June, consistent with being triggered by the two of them, and then the two December earthquakes are the same. So basically it looks as if we've got a whole sequence of triggered earthquakes. Okay, so that's great, and it tells us something, but could we have put a picture like that out right after the earthquake, and more importantly, could we put numbers to it? Because right now I haven't shown any numbers. I've talked about red areas and blue areas and an increase and a decrease, and it's all really woolly. Okay? But if we're going to do something about it really, we've got to put probabilities on it. We've got to say, what is the change in likelihood of these earthquakes? Okay? And that's where science is going on. This is what we're working on. So they've been doing this kind of thing for a while in New Zealand, and it really got ramped up after the Christchurch earthquake, because there was a huge interest in knowing what might happen next. Okay, and so this is a model called STEP, which is short-term aftershock probabilities, or earthquake probabilities. And these types of maps started being put out after the earthquake, where this is the likelihood of experiencing some damage. So basically, they took the likelihood of an earthquake above a certain size and translated that into shaking. How much is the ground going to move? And then they put out these kinds of maps. Okay. What I've been doing is I've been working with people at GNS Science and say, can we take these maps, and I should say, what I should say about these maps is that they're based purely on earthquake statistics. So they're based at looking at what the number size distribution is. In other words, for every 8, how many 7s, or in this case, for every 6, how many 5s do you see, how many 4s do you see, how many 3s do you see, how much the rate of activity has increased because you had the main shock, okay, whether it was the Darfield earthquake in September or the Christchurch earthquake in February. So it's based purely on observations, the beginning part of the sequence. Whereas the kind of maps that I make, the red-blue maps that you've seen, are based on knowing the slip of the first earthquake you're interested in. So what we're trying to do is we're trying to put these two approaches together. And so what we've got is we've got what would have been a symmetric pattern, and this is now a forecast of rates. So this is actually forecasting the number of earthquakes above magnitude 4 that you're going to get in a 100-day time period. And you can see it's asymmetric where there's an increased rate here and here compared to over here. That's the Coulomb pattern. That's that stress pattern that comes out of the work that I do, superposed then with their statistical model. And so we're in the process of refining these models and of testing these models. And I'll show you a result in a minute which shows that this approach is actually fairly valuable. But I just want to talk a little bit about where it's going. Because right now we're making these maps, but what we're not doing really is talking about faults. So, this is the Cook Strait sequence, and this happened in 2013. There were 2 magnitude 6.5s in the Cook Strait between the North and South Island in New Zealand. Red here are fault zones that experienced positive stress from the first one. Blue are ones that had negative stress from that. And you would think, well, if you know the faults are there, then you should resolve the stress on the faults as opposed to making these maps. This is the second earthquake, and it didn't happen on any of the map faults. And that's something that's very common in New Zealand. Only about half the earthquakes happen on the map faults. It's very common in Adelaide as well. There's not a strong correlation at all between the map faults. And so what we'll probably have to do is have some combination of map faults and these maps that we make, these surface maps or aerial maps that we make, okay? And these things are called ensemble models. They're used in weather all the time. So if somebody's forecasting a tropical cyclone and where it's going to go, they don't have one model that tells you the path of the tropical cyclone. They have 5 or 6 models that are stacked with each other based on their skill, based on how well they've done in previous situations. And so that's one place we're trying to go. The other is about understanding earthquake geology. This is back in Christchurch area again. This is the Darfield earthquake, the first one. This is the Christchurch earthquake that did so much damage. This is the Porter's Pass fault, which is a known fault capable of having a magnitude 7 to 7.5 earthquake. There's a big increase in seismicity on that fault after the Darfield earthquake, but nothing big. Nothing above about a 3.5, I think, okay? In other words, that fault zone, for whatever reason, wasn't ready to go. Those earthquakes started but didn't grow very big. Okay? And is there some way we can incorporate knowledge of the prior history of our faults into these models and again, add it to the ensemble? So that's, in terms of the science, where I'm trying to go, working with people in New Zealand and elsewhere. Where we're moving as a community, and I'm part of this, is into something called operational earthquake forecasting. And I'll give you the context for that in a second, but I just want to show you, this is an example from a guy called Werner Mazzocchi in INGV Rome, and he's got live a system now purely based on statistical methods, but it's an ensemble model, and he can say, how does the probability or the forecast rate change with time as you get these little earthquakes happening, okay? He hasn't gone live with it though. He's got this, he's developed it, he's got this wonderful, wonderful interface, and he hasn't gone live with it. I'll come back to that in a second. This is the most recent test of these types of models, and there's a whole series of them here. This is my model, step plus Coulomb. These are a bunch of statistical models here, and these are a bunch of Coulomb-based physical models as well, using these stress patterns by a crowd at GFZ Potsdam. And what you can see, this line here is random. Okay, so if your model is worse than random, I don't even know what it is. Earthquakes aren't random, they cluster in time and space, that's what aftershocks are. So you've got to be out here somewhere to be doing better, to have any reality to your model. All the statistical models tend to line up kind of over here, and then quite gratifyingly, the physical models are beating them, okay? So it suggests that having more physics and more understanding what's actually happening in the world in these models does better than purely looking at the stats. Now, we won't talk about the fact that GFZ's a little bit further over to the right than mine, but, this is where we're going, and I think that there's a lot of hope in that. And so I think that over the next few years that we really will refine the science, and we'll get a lot more confidence in our models and be able to really put these things out in the public domain rapidly, maybe automatically, like using a type of system like Werner's at INGV. There's a problem, of course, and the elephant in the room is L'Aquila. And I don't know how many people here know about this, but basically there were 6 earthquake scientists and a guy from Civil Protection who were convicted of manslaughter after the L'Aquila earthquake. Initially, there was discussion about whether they should have predicted it. There was a ground risk, or there was a commission put together to talk about prediction, and I'll show you something that came out of that in the next slide. But in the end of the day, they were convicted of manslaughter for not communicating properly the risk. And as you can imagine, that has scared earthquake scientists around the world. That conviction has been overturned now on appeal, although not for the civil defense person. So he's still looking at a couple years in jail for manslaughter, and I think he's got a second appeal that's coming up. So this kind of shocked the whole community. I mean, you always know that you can get sued, but that's what indemnity insurance is for. But manslaughter is something else. So this is work from led by Tom Jordan, but involving others. And this was after the L'Aquila earthquake, and trying to investigate basically prediction and what can be done, et cetera, et cetera. And out of this came this call for operational earthquake forecasting, for having short-term probabilities of future earthquakes, authoritative, scientific, consistent, transparent, and timely. Okay. The authoritative scares us all a bit, because we're not quite sure what Tom meant when he wrote those words and everybody else signed off on it. Because authoritative in terms of it's the best science we can do, that's okay. But we're talking about very low probabilities. And so we might be in a position where the background probability for magnitude 6, and I'm making these numbers up, okay? So, but the background probability for 6 in Wellington might be 1 in 10,000. And then something's happened in the Cook Strait, and there's been some stress changes, and it's increased that likelihood to 1 in 500. That's a huge change in likelihood and probability, but the absolute value is very low. And so if I go out and I say, okay, now I think you should take action because there's a 1 in 500 chance that there's going to be magnitude 6, I don't know how to communicate that message. I would take action based on the change from 1 in 10,000, but I'm going to be wrong most of the time. Most of the time, nothing's going to happen. Okay, so how do we communicate that? This is stuff, again, Werner's working on in Italy. He hasn't sent it live. When he does, his feeling is he's going to have absolutely no commentary. They're the raw numbers, and that's it. And if I lived in Italy, I would probably do exactly the same thing. This is also from Werner, and his description of it is, here's the way scientists view the world. We have lots and lots of things that could affect our numbers. We have large uncertainties in all these numbers, and the public officials and the public maybe want one number. And back to what we see with the tsunamis. I'm a little bit less skeptical. We had a meeting about this in a lovely place in Italy in June, and it was on operational earthquake forecasting, but also decision making. And that was a big part of it. And about a third of the meeting was about, okay, if we can make these probabilistic estimates and we can do it with good science behind it, how do we communicate it? What do we do with it? And lots of arguments. Will people understand the difference between the risk of driving their car versus flying? Except, do they? Because there's so many people, there are people that are absolutely terrified of flying, even though it's very much safer than driving the car. People say, well, we go to the doctor, and the doctor says you have X chance of surviving this. Do people really understand it? And do people understand it when you're talking probabilities of 1 in 500? I don't know. My personal feeling, and I proposed this at this meeting, and everybody thought I'd get sued, was that we try to empower citizens as decision makers. And I'll give you an example from Wellington, which is a city I love. I don't know how many people have been to Cuba Street, but Cuba Street is this really lively area. There's lots of bars and cafes and restaurants and whatnot. Part of it's pedestrianized and part of it's kind of semi-pedestrianized. And this is just a nightlife scene from Cuba Street. And it's got some really scary buildings. So these are heritage buildings, what they call, okay, this is unreinforced brick. And I couldn't find it, but I have a picture around the side of that, and it is just unreinforced brick. So big earthquake comes, 7.5, and that building's probably going to fall down. Okay. And when I visit GNS, we talk about what are we going to do if you're on Cuba, what do you do if you're on Cuba Street and an earthquake happens? And the answer is you run inside. Seriously, because Cuba Street is going to get filled with bricks. So you run inside and you hope the building that you run into doesn't completely collapse. Okay. And I've been sitting there drinking a pint, looking around me going, okay, where am I going if it starts to shake? Okay. So the other thing they have in Wellington is they have an earthquake-prone buildings list. Okay? So you can go online and you can get the addresses of all the buildings that have been identified as unsafe in large earthquakes. The problem is it's not very user-friendly. It just gives you the address. So it might give you 123 Taranaki Street, and I have no idea if that's Molly Malone's, which is on the corner of Taranaki Street and my mind's gone blank, and another road. So it doesn't do a lot for me. So what I would suggest, and I did suggest this at the meeting, is why don't we put out the probabilities, put out the change, and then put out a map of earthquake-prone buildings and let people make up their own minds. And then back that up with an education campaign, starting in schools, high schools, to the public, et cetera. I don't know. Like I said, people shot it down because they figured we'd get sued, and you know, because business owners in Cuba Street would sue us when nobody went to Cuba Street for a month and no earthquake happened. So it's tough. So trying to put it together then, prediction as in next Tuesday, 2 o'clock, almost certainly impossible. I would say it's impossible. Yeah, right button. But we're making a lot of progress in terms of this operational earthquake forecasting, of being able to, in Tom's words, of making authoritative and scientific estimates of short-term probabilities. And I think over the next few years, these things are going to start to be quite common, that the numbers will be out there, but maybe not with any commentary, that you'll be able to go on websites. And GNS Science in New Zealand's really pushing it. Italy's not too far off except for the political issues and the scare issues. The Coulomb stuff looks really interesting, and not just because it's what I do, but the fact that the physics-based models seem to be outperforming the statistical models is really promising. And the reason it's really promising is that I think the Coulomb stuff gives us a better handle on big earthquake triggering. So we go to aftershocks because there's lots of data. But in the end of the day, you want to know, Nepal just happened, it was magnitude 7.8. It triggered that 7.3, but what's going to happen to the west? And what is the change in likelihood to the west of that earthquake? Can we put numbers on that? I can't right now, but I'd like to be able to. And then what I said, communicating this is probably going to be really, really challenging. Thank you.
Okay, thanks, Sandy. We do have some time for some questions, if anyone has some. There's some microphones about.
Thank you for an interesting talk. I became interested in earthquakes a few years ago because of volcanoes and climate. There are far more earthquakes than volcanic eruptions, so in an area it's useful to look at the earthquakes. One of the things that struck me about that Sumatra earthquake was there was a huge increase in small earthquakes up to a decade or more before the actual big one happened. Have you looked at precursors or earthquake swarms?
I haven't, but people have looked in general at this, and they call them foreshocks, just like you have aftershocks. But so there are earthquakes that occur. What people don't show very well is a causal relationship. So you know, you can. What we know is that every earthquake triggers other earthquakes. And most of the time, simply because you have a lot more small earthquakes and you have big earthquakes, and most of the time the earthquakes that are triggered are smaller. But every now and again, you just pull out of a lucky bag, as a friend calls it, you pull out a bigger earthquake. And if that happens, somebody calls it a foreshock. You know, so my personal feeling is that there's no physics behind something being a foreshock or an aftershock. It's just the luck of the distribution.
I was going to talk about politicians and earthquakes, but when you mentioned lawyers and earthquakes, it's even more scary. The Christchurch example, my naive understanding was that initially, when they went to rebuild the city, the CBD was the most earthquake-prone area, and the parklands and green area around was non-prone. So the original suggestion was rebuild the city out there and leave the CBD and make it parks. However, politically they got overturned and they've gone back to rebuilding the CBD. So the whole point I came along was to think about the actual prevention rather than cure component of it, as in Cyclone Tracy in Darwin, for example, where now the building codes mean every building has to have a cyclone-proof core.
Yeah.
So do you know more about that?
I don't know enough about about the CBD and the decisions there. What I do know is that along the river Avon, is it, that meanders through there were houses that were badly damaged about 3 homes back, and they had very bad liquefaction in every one of these earthquakes, including some of the smaller ones, some of the 5s and 5s and a halves. And so they've condemned a whole swathe of houses there and are turning it into a reserve. Now there's a lot of politics around insurance, and there's some really serious insurance issues there. In terms of the CBD, if they're rebuilt, well, they are rebuilding there, they're going to have to build much better structures. And there are different ways you can do that. One is you can go deep, and so if you can get through the liquefaction layer and put the building on stilts that are in much more solid rock, then it's not going to be affected by the liquefaction. And any place that's prone to liquefaction, you're going to have to do that. The other, if you're not worried about liquefaction, but you're just worried about strong shaking, and Christchurch had some extremely strong shaking in the February earthquake, then you can do basal isolation. And so if anybody's ever been in Te Papa Museum in Wellington, for example, there's a place that you can go down, and it's on these rubber blocks. And the idea is that the earth moves and the building stays steady. So there are engineering solutions, but they cost a lot of money. And if they're going to rebuild in a very earthquake-prone area, I think they're just going to have to spend the money.
I suppose my question follows on from that in the sense that when you're dealing with these kind of events, you're dealing with something which is inherently hard to predict in the long term, and the ability to strengthen a lot of these buildings to resist that can be quite costly. So you're dealing with a situation where it's hard to say to someone, you must spend this money to bring your building up to scratch for an event which may not occur. Is there a method in your research that helps aid, I suppose, the policymakers and the potentially even the insurance companies in saying, this is the reasons why we feel we need to implement these kinds of restrictions, put encumbrances on properties or incentives into actually strengthening this older structures?
Yeah, it's a really good question, and it's something I probably should have brought out in my talk, because this idea of operational earthquake forecasting can actually help with that, because it is short-term to medium-term changes in seismic hazard. So it's not the plate tectonic map, every place in red is dangerous. It's some places are now more dangerous than others. And so in Turkey, for example, the İzmir earthquake in 1999 triggered the Duce earthquake to the east, but it also increased stress to the west in Istanbul. And our braver scientists than I am actually put out a forecast saying that there was a huge increase in the likelihood of a magnitude 7 earthquake there. And as a result, the Turkish government have put a lot of money into trying to make Istanbul less dangerous. And so they're actually moving people out of unsafe structures. They've forbidden some types of building that they were allowing previously. So they've identified that, and they've actually put out kind of emergency kits so that there are places that you can go and get picks and shovels and things like that if there's an earthquake and buildings fall down. So they put a lot of money into it. Now the danger is that they're still waiting for that earthquake, but it's made Istanbul a lot safer. So I think that this type of science that I'm describing, it can help you focus in on where you prioritize, and maybe it can help concentrate the minds of building owners as well. And if you did what I suggested for Cuba Street, does it give the people in Cuba Street an incentive to shore up their buildings so that the next time there's a seismic crisis, the people don't stay away from their shop?
Yeah, great talk, Sandy. Thank you. I was just going to, just for the people, the Newcastle earthquake was not a very large magnitude earthquake, but it caused a lot of damage, I think, because of the depth of the epicentre. I thought you might just want to quickly comment on that.
I'm too new. I'm going to pass on that one completely.
Well, only that the depth of the epicentre...
Oh, shallow, okay.
Yeah.
It was very shallow, sorry. I looked up that earthquake, but not in any detail, because I've only been in the country 5 months. But yeah, basically the depth makes a big difference. And so that was part of Nepal as well. It was a fairly shallow earthquake. So essentially you get attenuation, you lose energy as you go up through the surface layers. And so if the earthquake's very deep, then it doesn't shake nearly as much as if it's very shallow.
Hi, Sandy. So has anyone ever looked at earthquake prediction in idealized cases where, for example, you just build a model of some interacting system in a computer where you know what's going on, and you might get earthquakes as some sort of emergent behavior, and then you actually see if you can predict it even in an idealized case before you actually go to the real data?
Yeah, what happens is that you either, when you build earthquake models, you either get models that give you perfect periodicity because you get essentially stress concentrations that break everything, in which case it becomes perfectly predictable, or you tend to get behavior that gives you this power law behavior, the magnitude size distribution that we talked about, and in that case you don't have predictability. And it's not my stuff, but a colleague of mine actually compared earthquakes to chaotic systems and concluded that earthquakes were less predictable than chaos.
One thing you haven't talked about, Sandy, there are a lot of stories around that animals can detect earthquakes before they happen. And certainly in some of the geophysics that I've read, there's a belief that earthquakes might actually generate electrical signals as well as seismic signals, and that's actually what the animals are detecting. Have you heard anything about the electrical side of earthquake prediction?
Okay, there's two separate issues there. In terms of the electrical stuff, the worst conference session I ever went to was in Boulder, Colorado in the late 90s, and it was all these people that were really into earthquake prediction. And so they were throwing out every precursor that they could, and one was the electromagnetic stuff. But the problem is they would show these plots, and they would show, here's the signal, boom, here's a change in the signal. But every time they had that boom, it was right on top of the earthquake. So it was co-synchronous. It was at the same time as the earthquake. It didn't precede it. And I've never seen anything convincing saying that you get a precursor, a demonstrated precursor. One more general point about precursors is that it's really easy to do case studies and to go to an earthquake and say, okay, let's look at everything that happened before this earthquake. And anything that looks a little bit weird, we say that was a precursor. But what they never do is then they say, well, let's take that phenomenon that we think is a precursor. Now let's go through the entire period of time of that area, and how many times did we see that signal and we didn't get a big earthquake? Okay, so a lot of the prediction, I'm on my high horse for 30 seconds. One of the problems with the prediction people in some countries is that they get money by going straight to government by saying we can predict earthquakes. And they use some fairly dubious data to support that. In terms of animals and stuff, I would ask the same thing. How many times does your cat act weird and there isn't an earthquake?
Okay, that might be a good point to wind things up. I have a gift, Sandy.
Oh, thank you.
There you go. Enjoy that.
Sure I will.
Can you please join me again in thanking Sandy for her talk tonight. And just very briefly before we wind up, I'd like to let you know about our next Research Tuesday event. In 2 weeks' time, we'll be hearing from Dr. Kerry Wilkinson from the School of Agriculture, Food and Wine. Her talk, titled Smoke in the Barrel, will discuss the effect that bushfires can have on grapes and wine and what our research is doing to address it. That's on Tuesday, June the 9th, and you can register on our website. Thank you all for coming tonight. I wish you a good night.